Okay, we're going to talk about covalent bonding with atoms which end up having more than 8 electrons in their outer shell. Now, I realise this is a bit of a departure from GCSE, where we always said 8 electrons was a full outer shell, and everything is aiming to to get that. So yes, it is a little bit of a departure, but let's just have a look at the periodic table. Now, if we look at period 1, period 1 only contains hydrogen and helium. So the maximum number of electrons you can have in is, because the first shell, period 1, is max 2 electrons, okay? And that's why it's a very short period. Okay, now when we go to period 2, we know there's room for 8 electrons in period 2, because we have got lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Okay, that's 8. We've got 8, and then that is full up, so that's a maximum of 8 electrons. Period 3, let's have a look at period 3. Now, this is where it gets a little bit complicated, because, as we'll see in a later topic, there's actually room for 18 electrons in period 3, because you've got sodium, magnesium, and then also this is called the D block, and there's room for 10 electrons there. So there's room for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There's a maximum of 8 electrons you can have in if you are talking about period 3, because we're talking about shell 3. There is a max, so there's room for, not 8, sorry, 18 electrons there. And period 4, if you wanted to look at that, that's a bit more obvious. Period 4, there's room there for 18 as well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There's a maximum of 18 electrons in that one as well. Okay, what does this mean for covalent bonding then? And I realize that this may be slightly confusing, but you will, in the first few weeks of year 12, you will do a little bit more about the electronic structure, and you'll realize why period 3 has got room for 18 electrons and not just 8, period 4, 18 electrons, and so on. So if I do that, and then I'm going to put in my little you're going to put in a staircase line to separate the metals from the non-metals, so that goes in there. Okay, so everything to the left of this line are all metals. So generally speaking, we are not worrying about them forming covalent bonds. So we are concerned with this block at the top right-hand corner here. We're concerned with all this lot. The noble gases I'm going to leave off for the minute, because, well, actually I should really, because krypton and xenon definitely form compounds, as we'll see later. Argon will form a few compounds that are only stable around about absolute 0, but nevertheless that will form compounds as well. But really, I suppose we're concerned with all this yellow lot of elements here. Now, any element in period 2 can only have a maximum of 8 electrons. Okay, so I'm going to rub this off here. Period 1, obviously 2 electrons. So anything in period 2, you've got a max of 8 electrons when it ever does covalent bonding. But period 3 has got a maximum of 18 electrons. What does this mean for us? Well, it means when we're talking about, let's get rid of some of this, and anything in period 2, and these are the most common things that we're dealing with. So we're dealing with carbon, nitrogen, oxygen, and fluorine. Yeah, all of them, maximum of 8 electrons in the outer shell. But there are some important elements in period 2, in period 3, which can have more. And notably, the most important of those would obviously be sulfur, phosphorus, and chlorine, which we deal a lot with. Yeah, so they can have a maximum of 18 electrons. These other elements here, so all this lot here, these can obviously have 18 electrons as well. Arsenic, selenium, tellurium, we're not so concerned with them, really, are we? But bromine and iodine, yet we deal with a lot of compounds of bromine and iodine. So, and we need to remember that they can have a maximum of 18 electrons also. So let's start by having a look at some compounds of, I think we'll look at sulfur first of all. That's really important. And then we'll have a look at phosphorus and then chlorine as well. Okay. So sulfur compounds. Most of them end up forming sulfur ends up with more than 8 electrons in its outer shell. Let's think about one where it doesn't. This is H2S. That's a very similar similar to water. Right, we've got to think sulfur is in which group of the periodic table? It's in group 6. So it's got 6 of its own electrons in its outer shell, but it can fit up to 18. So H2S would look like this. A dot and a cross there, a dot and a cross there. Sulfur's in group 6, I've only drawn 2, so 2 lone pairs. So H2S, very similar electronic structure to water. Let's have a look at this one though now, SF6. And we'll see here that sulfur has, in this compound, sulfur is going to have, well, it's got 6 of its own electrons, and each of them forms a pair, so it ends up with 12 electrons in its outer shell. So SF6 I draw, right, and I need 6 of them, 1, 2, 3. So there's sulfur in everyone there. It's got a dot and a cross, a dot and a cross. Sulfur hexafluoride, and all these are F. Now, I'm not going to draw the electrons for every single F because I'll be there all day, but fluorine is in group 7. I've only drawn 1, so I need to draw 6 more, so it would have 3 lone pairs there, and every other fluorine is going to be the same as that. So that would be the electronic structure of SF6. SF6 is a very heavy gas, and I think I always seem to see that it's the gas that makes your voice very deep. If helium makes you, it's a very dense gas because it's got a big molecular weight, and helium, if you breathe it in, it makes all your voice all squeaky. Well, apparently if you breathe this stuff in, I've never tried it, it makes your voice very deep. Right, so that's SF6. Sulfur is again, right, just the important thing about the electrons, isn't it, is there are 6 of sulfur electrons, each one is paired up to form a covalent bond, so you end up with 12 electrons in the outer shell. That's quite an obscure compound, but some of the other things, let's think about that are much more common. Let's think about sulfuric acid, H2SO4. And here we see, again, sulfur is going to have 6 electrons in its outer shell. So let's just erase all that, and we'll draw the electronic structure of sulfuric acid. So we've got H2SO4. And the bonding in sulfur, so sulfur, it's in group 6, but it can actually form 6 bonds, as we've seen. So the sulfur is going to form 6 bonds. Oxygen is in group 2, that can't have any more than 8 electrons out of the shell. It's in group 6, but it can only ever form 2 bonds. And hydrogen, of course, always forms 1 bond. So sulfuric acid is, you have, and then these oxygens are attached to the hydrogen. Hydrogens. Okay, so that is H2SO4. Incidentally, you only get this covalent molecule in pure concentrated sulfuric acid. When you put it into water, we'll see what happens in a minute, but that's, well, you know what happens already from GCSE, it dissociates, doesn't it? But anyway, let's draw a dot cross diagram for that. So we're going to have sulfur here. Let's do the oxygens in red. And we've got our hydrogens in blue here. So double bond, this one is a double bond, so we're going to get 2 electrons from the oxygen and 2 electrons from the sulfur. Same with this one here. These are single bonds, so you get 1 electron from the oxygen and 1 electron from the sulfur. And these are single bonds to the hydrogen, so you get 1 electron from the hydrogens and 1 electron from the oxygen. So let's fill in the electrons that we're missing now. Let's look at sulfur first of all. Well, we've got 6 electrons in sulfur, and we've got 1, 2, 3, 4, 5, 6 already. So we don't need to add, there's no lone pairs on the sulfur. The oxygens, these oxygens here, 2 electrons, so there's 4 left over. So there's 2 lone pairs on these oxygens. Likewise, with the oxygens forming single bonds, 2 lone pairs to make up 6 electrons. And the hydrogens are fine. So that is the dot cross diagram for sulfuric acid. We can see that the sulfur doesn't have 8 electrons in its outer shell. It's got 12. All 6 electrons have been involved in bonding. Each one's forming paired up with another electron. So you've got 12 electrons there. And let's think about, well, we know, well, sulfuric acid is a strong acid, and we've always said what happens is at GCSE, H2SO4, you put it into water, what happens? You get 2H plus, and you get a sulfate ion. Okay, let's just see how that happens. Well, these blue hydrogens here, they are going to go away, but they leave the electrons behind. You've got those 2 blue electrons now on the SO4 2 minus. That means that the whole thing has got a 2 negative charge on the sulfate ion. And again, I always point out with that negative, the 2 minus is not just stuck on that electron there and that electron there. The 2 minus charge is spread over the whole thing, and that makes it that makes it a lot more stable if the charges can spread out. And there's your sulfate ion. And I said, really, so we said our hydrogens are going to drop off there as H plus and H plus. Drawn there, but this, as I said in a couple of videos back, the hydrogen ion H plus doesn't really exist, does it? Because I have no electrons. It has an incredibly high concentrated positive charge, be tiny, just be a proton. So, well, we know really that this is shorthand for H3O plus, don't we? Okay, so what really happens, if you want to write the real equation, is sulfuric acid reacts with two waters, and each of those waters becomes an H3O plus. There's a dated bond in this thing, remember, a dated bond, and you get your sulfate there. And it's worthwhile mentioning this just at A level. Really, we say that acids are proton donors, and the converse of this are bases are proton acceptors. That's a little bit different for GCSE. At GCSE, we said that acids are things which make H plus ions in solution. Now it's better to start thinking of them like this way. Acids are proton donors. So why is the sulfuric acid acting as an acid? Because it's given away protons. Who's it giving the protons to? It's giving them to the waters. Okay, so the water has accepted a proton, so the water has acted as a base. Okay, so whenever you have an acid giving away H pluses, you've always got to have a base accepting them, because of course H pluses can't exist. Protons cannot exist by themselves. So that is our sulfate ion. And remember when we first of all started talking about polyatomic ions, and I said I'd talk about sulfate later. So this is the electronic structure of the SO4 2- ion. So the sulfate ion is made up of one sulfur atom covalently bonded to 4 oxygens, and it's got a charge on it because it's got two more electrons than it should have to balance the number of protons. Of course, these electrons, if you like, they've come from these hydrogens here. So that is sulfuric acid. While we're here, let's just talk about phosphoric acid, which we don't really need to know about, but it's and so if you like, you can fast forward this bit, but let's just have a think about phosphoric acid. Right, phosphoric acid has got the formula H3PO4. The phosphorus is in group 5, and it is in period 3, so that means it is allowed to have more than 8 electrons in its outer shell. Now, phosphorus forms a lot of compounds, and each of its 5 electrons pairs up with another one to form a covalent bond, so it forms a lot of compounds which are with 10 electrons in the outer shell. Okay, so the simplest of those, I think, would probably be PCl5. So phosphorus actually forms 2 chlorides. It forms PCl3 and PCl5. So PCl3 only has 8 electrons in that shell. So if I draw that, we've got P. I'm going to have 3 chlorines here. Right, so what do we draw? We draw a dot. These are all chlorines, yeah. A dot and a cross, a dot and a cross, a dot and a cross. There's 5 electrons in phosphorus. I've only drawn 3 of them, so it has a lone pair there. Okay, and that's exactly what nitrogen would do. So nitrogen forms NCl3, yeah. Nitrogen is in group 5. That's what nitrogen does. But phosphorus, what also can happen is these two, instead of having these as a lone pair, each of those can split up and form a separate covalent bond. Oh, sorry, really what I should do is I should put the electrons in those chlorines. They're in group 7. Yeah, I'll just do one of them. So that's PCl3. Let's see what happens with PCl5. That pair of electrons are going to split up, so you get 5 chlorines. In each one, you get a dot and a cross, dot and a cross, dot and a cross. Okay, now we've accounted for all 5 of phosphorus's electrons there, so there are no lone pairs, unlike PCl3, which does have a lone pair. It's got 5 bonding pairs, and it has 10 electrons in its outer shell. And it's allowed to do that because it is not in period 2, it's in period 3. Nitrogen, on the other hand, you can only get NCl3. You can't get NCl5 because nitrogen is in period 2, and you're not allowed to have more than 8 electrons in the outer shell. Okay, so that's PCl5 with 10 electrons in the outer shell. Let's draw phosphoric acid now. So, which has also got, phosphorus has got 10 electrons in the outer shell. Phosphoric acid, and that's quite important in biology, of course, because it's in DNA and stuff, isn't it? So we've got phosphorus forms a 1 double bond to an oxygen. We'll see that phosphorus likes to form 5 bonds when all the 5 electrons have been used, and it ends up, and it's got 3 of these here, like that. Okay, so you can see the phosphorus is forming 5 bonds. All the oxygens are all forming 2 bonds, which is what they like doing. And let's just draw a dot cross diagram for that then. So there's our phosphorus here. Oxygen will do in red again. And our hydrogens in blue. Oxygen. Right, so this one here is a double bond. So we have 2 electrons from the oxygen, 2 from the phosphorus. These are singles, so 1 from the oxygen and 1 from the phosphorus. Single bond to the hydrogen, so 1 from the oxygen and 1 from the hydrogens. Those oxygens need some, the phosphorus doesn't need any lone pairs, because look, we've got all 5 electrons, 1, 2, 3, 4, 5, all accounted for, so no lone pairs. But the oxygens, they've only got 2, so they need 2 lone pairs each, because they've got 6 electrons in their outer shell. So that would be the formula of the phosphoric acid. And of course, when it acts as an acid, it's called a tribasic acid. You probably can see why it's called tribasic, because it's going to lose 3 protons. So H3PO4, and it's going to lose 3 H pluses, and it's going to form a PO4 3 minus ion. Now you can see how that forms. All of these hydrogens here, they're going to go, but they leave their electrons behind. So you've got 3 extra electrons there. And that, of course, means the overall thing has got a -3 charge on it. And this is the phosphate ion, the PO4 3 minus. So if you had a like sodium phosphate, because sodium is Na plus, well, the formula of sodium phosphate is going to be Na3PO4, isn't it? So if you like, phosphate's got a valency of 3 there. Just to remind ourselves, of course, really those H pluses don't drop off, do they? What happens is they are given away to water molecules, and you're going to need 3 water molecules. And you're going to get 3 of the H3O plus ions with the dative bond in there, and the phosphate ion. Okay, so that ends the story really, but we know all of those polyatomic ions. Now we know the electronic structure of them all. We know OH minus. That was easy, wasn't it? We know carbonate. That was relatively easy. CO3 2 minus. We know nitrate. That was a bit trickier because it contained a dative bond in the nitrate. Now we know the sulfate ion. That's a bit trickier because the sulfur has more than 8 electrons in its outer shell. And we've even done phosphate, and that's a bit tricky because that's got more than 8 electrons in the outer shell. And of course, we did NH4 plus as well, which has got a dated bond in, so we couldn't do that one straight away because we didn't know what a dated bond was. But now, hopefully, we know all of these quite important inorganic ions. Oh, another one which we've forgotten about, another easy one, the the hydrogen carbonate ion, so that's the HCO3 ion. We know all of those important inorganic ions. we know the bonding in them, and they're not just like magic numbers now. And like GCSE, people always get confused. Like SO4 and 2 minus, they think, oh, it's got a -4 charge or something, and 2 oxygens. It's not, is it? We know what all that means now, hopefully.